All right. So first, I will introduce myself. So this is Vijay Rahane. I'm a Prime Minister Research Fellow in IIT Delhi, and today we are here to discuss some problems based on the week 12 content, which is covered by the professor. And generally, we are not only looking for the week 12 content. We are like a kind of discuss the some examples and which involve which is comes from the this entire course of this essential of oxidation reduction and carbon-carbon bond formation reaction and its application in order synthesis. So basically, we are looking for some examples. So in which new carbon-carbon bond is getting formed or bond is getting cleaved, some oxidation reduction or reduction reaction, and many more reactions. So basically, we are look today we will look for some examples. Uh, so that will be based on the real life application of this of our organic synthesis, right? So before going to start the session, so does anyone have any doubt regarding the topic or this entire course? Because this is the last, so this will be the last video of this course, and uh, and today we'll see entirely we'll revise the entire course. So So this is the last session, and today we'll discuss the problem based and discuss the if anyone have any doubt regarding this course content or any topic, so that we can discuss now. So if you have any doubt, you can stop me in between, or also you can put your doubt in the this chat box so that we can discuss in the later. So today to discuss some examples, I have taken the one of the examples of the total synthesis from this paper. So which is comes from the Journal of American Chemical Society, which is published in 2010. And so this is the you can refer this. So this is the reference you can refer from this one. So here, so you can see here. So this is the just conversion that I have given particularly, and so in this one you can see there are multiple steps are involved. So to convert this compound 13 to the compound 14, so what kind of reagent that you need to use here? So that's the question. Further, from 14 to 15, so also there is a group of reagent. So basically, I will directly take the reaction condition, so that will be easy for you to understand. So what is the condition here for to perform this reaction? So if you look at the first step, so which reaction it is? So this is basically Birch reduction reaction, and so since it has the electron rich group like this oxygen O tips and O methyl, sorry the methyl. So the reduction goes in the manner. So this is the product of this Birch reduction reaction. So here the reagent is the sodium in the liquid ammonia, right? So these are the reagent used for this conversion, and you can see the product which is formed in this step. So the first step is the Birch reduction reaction, and the first one, that is the A, will be the sodium in NH3, and obviously after this is after 15 minutes, 15 to 20 minutes, need to add the third butanol, and the reaction solvent was the THF, right? So in the THF, and also the condition, if you look at the temperature, the reaction perform at minus 78 degrees Celsius, then to the room temperature, and then So this is the reaction condition for this one. So this is if for the detailed reaction procedure, you can refer the general always. So basically, here it's a Birch reduction reaction. So if you move from the 14 to the 15, so in this conversion, so what are the steps involved for this conversion? Is the first step here. So it is ED mix beta and uh, this is the a kind of CH3 S double bond O and NH2. This is uh, the reagent, and you can see again there is this is the TBU O methyl, again TBU O methyl. That's like a butanol solvent, and at minus 78 degrees, minus 12 degrees Celsius. So at that's like below the room temperature, right? Minus 12 degrees Celsius. So in this uh, method, basically, what uh, what is did at this step? So there is ADMX beta. So that's we already seen the role of this ADMX beta, and basically the protection ADMX beta. What it will do? It will convert olefin and olefin to the corresponding diol, and particularly so it convert corresponding diol, and here in this case, so it selectively did the conversion of olefin to diol, and the next step is the protection of the diol, and how this protection of diol takes place. So to protect this diol, so added the 2,2 dimethoxy propane. So that's like this is the structure. So by adding this 2,2 dimethoxypropane, what we can do? So we can protect this diol. So in this case, so this convert first initially converted to the diol, and then the diol is converted into the uh, corresponding acetal by protecting these both alkoxy group. So in the next step, what has been done? So you can see here. So this tips is deprotected initially and followed by the formation of this uh, bond, right? So in this case, so what are the group of reagent they use? So the calcium cesium chloride. So basically this is used to deprotect the tips. Then this is the PHACCl. So this selenium phenyl selenium chloride. So this basically once this tips is deprotected, so this bond goes here, and from this one the SEPH is getting attached. And once this SEPH is attached, then in the next step, so what they have added, the E, it is a two step, right? D, the first is deprotection and the phenyl selenium chloride, so that get attached attack on the phenyl selenium chloride once this cesium chloride deprotect these tips, and then uh, added the H2O2 pyridine. So basically, this is like the a kind of again elimination reaction takes place. So if I just put one by one reaction on the slide, so you can better that will be easy for you to understanding. So the first step here, we already seen the mechanism with the first step, right? The first step was the Birch reduction reaction. Birch reduction reaction. So that's the first step. The second step is the basically the diol formation. Second step is the see the B. I will put it here B. So the B step is the so conversion of diol to the sorry the olefin to the corresponding diol, and then the C step is the conversion of this diol to protection of this diol by using this 2 propane diol. So that's like a diol protection takes place. So upon protection of this diol, So what happens? So these both diols are getting protected. And if you look at the third step, so this third step is the, sorry, so this D step is the, in the D steps, what happen? So basically, so tips reproduction, reproduction using the cesium fluoride. So this is the chloride source. This deprotected the tips. So once the tips deprotect, so again the pH, SC, Cl. So the negatively charged produced on here. So that's like attack on the. So you can see here. So basically, once this tips is deprotected, so negatively charged is formed. So that negatively charged O negative uh, goes in formation of the C double bond O, and further it attacks on Ac and this Cl get removed. So basically, so we get here, so this is the double bond and alpha there, the Ac pH group is attached. And in the next step, so what's happened in the next step? So in the next step, what happened from here to here? So basically we had now, so this intermediate, right? So that's the remaining group that will be as it is. So we had the Ac pH. Then we did H2O2, right? So upon H2O2, so that will go into the, we see in this type of elimination reaction, right? So it's the similar example of the selenium chemistry. So SeO negative, OOH, right? So that's the form. And then further, basically, this is the, uh, this gives the elimination. This remaining groups will be remain as it is. So basically, this is the kind of elimination reaction takes place. So this is the E steps, right? And now in the next step, you can see. So what is the next step? So the next step is the, this entire across this group there is addition of this TMS, CH2 TMS. So how this addition takes place here? So you can see. So what are the reagent they have used to perform this addition? That's the F steps. So you can see here. So this is the TMS CH2 MgCl, and in presence of copper iodide. So as this I have already mentioned in the last video. Sorry, probably I haven't shared the screen, so probably I need to again mention this one. All right. So basically, all right. I will show that one. So basically, in this one, if you just look at here, so here, what are the steps involved for the in the given transformation? The first step was the Birch reduction reaction. Upon Birch reduction, it forms this double bond. So this aromatic ring get reduced. The next step is the B step is the B step is conversion of double bond to the diol by using the AD mix beta. And further, the C step is the protection of the diol by using the 2,2 dimethoxy propane, right? So this is the C step. The fourth, the D step is the deproduction of strip, the tips deproduction by using the cesium fluoride, and followed by the, obviously this is the source of electrophile. So this electrophile get attached at the alpha position to the this keto that newly formed. And in the next step, in the E that we added the H2O2. So upon adding H2O2, so this is the initially the step is formed, the oxidation of the selenium takes place and followed by the elimination. So it gives the alpha beta unsaturated ketone. And once this alpha beta unsaturated ketone is formed, the next step is now the addition of this TMSCH2 methyl chloride. So and in presence of the copper iodide. So we already studied the role of copper iodide in the last video. So this copper iodide makes this grignard as a soft nucleophile, and that's why the addition takes place at this fourth position, that is the alpha and the beta position of this alpha beta unsaturated alpha beta unsaturated ketone, right? And once this addition takes place of this grignard takes place here, so in addition what they have added, so they have added a TMS chloride. So what does this TMS chloride do? So once this addition takes place, so a nucleophile this nucleophile attacks on this position. So this bond move to here and this goes to here. So and it attacks on the TMS chloride. So the TMS get attached here. And when you elevate the temperature and add this palladium acetate. So what does it do? So it will again this TMS get back to here and here addition of the hydrogen takes place. So in this uh, step, basically nucleophile this CH2TMS is added at the beta position of this alpha beta unsaturated ketone. And in the same step, what are the side products are from? So you can not the side product. So this is the another this comes from another step. So it forms this 17 as a product. And the next step for this synthesis is the reaction of this 17 and this 19 to form this step. So what are the reagent used for to convert for this step is the, if you look at the reagent combination to perform this step is here the H. So that's the TSET and the DCM at minus 78 degrees Celsius. It gives 89% yield of this. And basically this TASF ethyl, and this is the reagent which used to deprotect this TMS. And once this nucleophile is formed here, so if you look at here, so this methox group is attached over this TMS, right? So this is the one of the reaction they have performed. So which is not much trivial reaction. So I am also not aware about the which uh, how this mechanism of this reaction goes. But the detail is given in the paper that reference that I have mentioned earlier. And in the next step, so in the next step, they did the cyclization of this one. So how they did the cyclization? So to perform the cyclization, so they have added palladium acetate supported on the PPH3 and Ag polymer supported PPH3 and AgCO3 in toluene. So it gives the 66% yield of this product, cyclized product. So basically, they palladium acetate insert in between here probably, and then might be attacks here. So that's some sort of the concentrated mechanism. The reaction some sort of works with the some sort of concentrated mechanism, and it gives the formation of this cyclized product 21. And the next step was the conversion of the not conversion. So the next step is the TFN3, that is the N3 nucleophile. So this nucleophile attacks on this position. So this bond goes to here, this bond goes here. So in the some sort of this manner, so the reaction works and it gives the formation of the compound 22. That's the quinone, right? So you can see there at the para position, it's the quinone. So we can say it as a quino. And further, that's the K2M. That's the first step was the TIPS OTF, the dipia, dichloromethane at 0 degrees Celsius, then DMDO, dichloromethane, and methanol at 40 at minus 40 degrees Celsius. It gives 76 yield of these final products. Uh, so if you look at what are the steps involved here from here to here, so there are several steps that we can add here, right? These are the several steps to get this uh, kinamycin F. So to get this kinamycin F, so these are some other steps also involved. But in this synthesis, as we have already seen, so interesting too many steps, multi-step synthesis. How you can see here, the first step was the Birch reduction, then the olefin conversion olefin to the diol, and then protection of the diol, followed by the deprotection of these tips, then the addition of the electrophile, that is the SCPH, phenyl selenium dichloride, phenyl selenium chloride, how this get attached on the alpha position, and then followed by the elimination reaction to get this 16 product, and followed by further the nucleophilic attack with the Grignard, and here the use the by using the copper iodide to make it as a soft nucleophile. So the 1,4 addition takes place. So the addition at the beta position takes place here. So this is how these are the some beautiful synthetic steps involved in this synthesis that you can refer. And with this synthesis, as you seen, there are in this the F step, particularly the TMS um, TMSCH2 MgCl, that's the Grignard reagent, and how the activity of the Grignard reagent is tuned by adding the additive copper iodide. So that's why instead of directly attacking on the hard center, that is the carbonyl, this Grignard reagent added attack on the soft center. Further, we have seen here, particularly in this step, uh, in the first step here, the step H. So these two fragment, the 17 and the 18, is getting uh, attached together by using the TASF ETH, that is the TSF ETH stand for ethyl group reagent, and the same at minus 78 degrees Celsius. So it gives the 79% yield of the product. So in which you can see, so these two fragments attached directly to this directly together, and followed by the cyclization reaction by using this palladium acetate supported on the palladium. So palladium acetate and the polymer supported PPS3 and Ag, that is the silver carbonate at 80 degrees Celsius. So that was the cyclization reaction. So this is how uh, this is the first example that I have shown some step from the synthesis of the kinomycin, and there are again several steps are involved. So that again you can refer the paper to how the other remaining steps. Further, this is the example of the another paper, that is it is from the tetrahedron data back from the 2007. So in this paper, so particularly there are few steps that I want to highlight here. So the first step is the conversion of 11 to 10. So in this step you can see, so added the TBDMSCl in the imidazole. So and further the second step was the addition of the methyl, that's the MGBR, so that's the Grignard reagent. So how this works, so the TBDMS protect this alcohol at the first, and further this Grignard, this is the Grignard which attack on this amide, and upon addition, so it is getting from a ketone. So this is the ketone 10. So amide is converted into the ketone, and in this particular you can see this alcohol is getting initially protected. Why this is protected? Because this if you add this grignal is also basic in nature, grignal reagent. So it abstracts the proton, and it get the quench, the reagent get quench. In the second step here is interesting, which is the sodium borohydride and the methanol. So that's the reduction of the ketone. This is the ketone, and the reduction takes place here. So this is not a seroselective reduction. So the reduction takes place here. Further, the next step is the addition of sodium hydride and the CS2. So basically, and the methyl. So basically, this OCSME getting attached on the hydroxy. So basically, hydroxy will convert into the OCSME, and then addition of the AIBN and tributylene hydrogen hydride. So this entire group is getting removed, and here we have added the hydrogen. So if someone asks why we are not directly adding the uh, that is the NaNH2 in KOH, so that's also Ullquist reaction that can also convert this ketone to the CH2, but the sensitivity of this remaining side chain will be in that case will be compromised. So that's why we are not using the directly NaNH2 in KOH, or also there is group team in HCl, that that sort of reduction reaction. So that's the reason we need to go for the 1, 2, 3 steps long method. We need to adopt that one instead of directly using this NaNH2 in KOH or the team in HCl. Further, upon addition of TBAF, so it deprotect the TBDMS chloride, that group that we have added already earlier. So it deprotect this group. Now the alcohol is free, and further the reaction is the PPH3 and the PNBA and DIAD. So it's the Mitsunobu kind of reaction, right? And so basically, the stereochemistry of this entire hydroxy group is inverted here by using this Mitsunobu reaction. So you know the Mitsunobu reaction. So basically, we get the inversion in stereochemistry after Mitsunobu reaction, and depends upon the which nucleophile that we are using. We get the nucleophile here. So here, nucleophile is itself hydroxy group. So we get inverted compound, the hydroxy group with the inversion in stereochemistry here. Further, some step that I would like to show here from here. Particularly, this is the FeCl3. So in this case, the just deprotection of this diol, and further you can see this is the O3 DMS, that is the ozone-lysis kind of reaction, right? And what does this steps do? So it convert this to acid, and further in the same spot, because there was a hydroxy group, it get converted into the corresponding ester. So this is the, because it is O3 in uh, DCM and the methanol. So this is ozone-lysis. The olefin it get converted into the, this is the here bond cleavage takes place, followed by you get one group is the, so this is the R, right? And it they have the OH, so it gets cyclized again. So this is the acid group is getting formed in the ozone-lysis, and followed by addition of the hydroxy group, attack of the hydroxy group to the acid, it gives formation of the ester. Further, they have added the mom chloride. So obviously, the hydroxy group it is protected, so it converted into the mom protection, and further LiHMDS and the PHACBr. So LiHMDS, what it does? So again, it will do the attacks on the hydride. It's hydride transfer agent, right? It do the hydride, it transfer hydride to the, so in this case, so two possibility, either attack here, or yeah, here only one possibility. So but here in this case there is acyclic proton, so it abstracts the proton from here, it forms a nucleophile enolate, and further addition of this pH SC Br. So this nucleophile that enolate attack on the SC, and the Br get eliminated. So basically the first step is the this SC pH, and then So this is the remaining part of the molecule, right? And then the addition of H2O2. So H2O2 do this job, oxidation, and followed by elimination. So it's again the elimination kind of reaction that we have seen in earlier example. So this is how we can able to prepare the alpha beta unsaturated ketone or alpha beta unsaturated acid or ester by using this kind of method. The addition of the first add the SCPH and then the elimination by using the H2O2. So this is the interesting step that we already seen the example name reactions of this ACPH uh, use of ACPH in the various reaction, and here particularly for the elimination reaction. Then you can see here addition of the FeCl3. What does the FeCl3 do? It remove the deprotect this mom protection, and we get the free hydroxy group. Further, this free hydroxy group, the addition of the DBU-THF at RT. So this is the some sort of uh, this two that addition of this compound and again the reagent two. So this reagent two is the, I'm not sure what are the reagent, these two, but upon this coupling, this final that the natural product is getting from. So anyway, no need to discuss this one, but up to here, you can see how beautifully the structural modification has been performed, and the it involved multiple reactions and various protection, deprotection reaction, addition reaction, nucleophilic, particularly ozone lysis reaction. So that's also kind of oxidation reaction. Further, the substitution reaction by just adding the first formation of enolate, then PHSE, we are substitute the hydrogen with the phenyl SCPH group. So these are the some examples which are like quite interesting. Further, we can see such reactions in this paper also. This is the synthesis paper from the Journal of Natural Product, which is from the 2013. And you can see in this paper, so this is the DSC2 MGI. So basically, deuterated Mg with Grignard, right? And that obviously attacks on the, because of this copper iodide, attack on the beta position of this ketone. Further, there was like TMS OTF, triethylamine, palladium acetate. So basically, this entire reagent is gives the formation of this double bond across this ketone. The next step is the again TMS CH2 MgCl. So that's we have already seen. We do the CH2 TMS. So remaining step I think is similar as already seen in the last video. So you can see here in this case what happens. The this not this CH2 TMS is attacked at the beta position by the use of the copper iodide to make this as a soft center. There are some interesting steps here also. So here the addition of the TFA to deprotect this mom fluoride group, sorry, this mom protection. So you can look at that this one. Also the TFN3 that we've seen earlier, how this TFN3 attacks here, and in the similar manner here the group is attached. So you can refer this this paper for the further better understanding of the multiple steps involved in this reaction. Again, here there is, I have mentioned particularly the example of stereoselective reduction. So here you can see the compound 4 is stereoselectively reduced, that is using the L-selectride. This ketone is converted into hydroxy group by using this L-selectride, and you can see So it gives the 97, the first step is it gives the 87% yield of this, and the reduction is quite stereoselective. Further, this hydroxy group again protected using the mom fluoride, that's the already seen, and initially it is protected. And why they have protected? Because first is protected, again here deprotected. Anyway, so basically this mom fluoride is used to protect this hydroxy group. So here it is protected, but here they have added a TBAF in THF. So I'm not sure in this condition whether the mom fluoride is stable or not. And then in the next step, they have added the TSCL, that is this OR group. Oh, all right, sorry. This monochloride is stable with the TBF, but these are this the R, and this R is the TBDMS, that is the silyl group, right? So this silyl group is differentiated using this TBAF and followed by this once the this TBDMS get differentiated, then again it is protected with the tosyl group, and further added the FeCl3. So this FeCl3, upon addition, it gives the formation of this product. So you can look at the play with the mechanism, how this mechanism of this reaction works. Another example here is particularly in the similar manner, this tosyl chloride for hydroxy protection, then the TBAF, that is the deprotection of this OR, that is the R is equal to TBDMS, and this TBDMS group reprotected, you can see here. Here the ozone lysis reaction, so this group has been deprotected, and obviously upon ozone after ozone lysis, the addition of the methanol, so obviously acid is formed, again acid converted into the this ester, corresponding ester. And further in the last step, the K2CO3 and the methanol. So upon K2CO3 and methanol, that addition, so this acetyl protection get removes, and this both hydroxy group will be the free. So this is the plus 2,5 bis EP gono thylacine diol. So this is the some kind of either natural product or a drug molecule, so that they have synthesized. The next some examples is a really similar kind of the steps involved, so that we have already seen earlier. This is just a scale up that they have mentioned, and 60-gram scale, this uh, burst reduction they have performed. 60-gram scale, first step was the burst reduction that we already seen, then the dihydroxylation to get this product. Then the obviously this tips deprotection and formation of the double bond. Further, the next step is the uh, dihydroxy protection, followed by the nucleophilic attack or the beta position of the. This is also some similar kind of work, and this TAS EFET that someone has asked earlier. So this is the reagent. You can see the full structure of this reagent. So basically, it is a silicon-based reagent with the 5 bond attached, and you can see that's the reason it has the negative charge, and the S NH NET2 thrice, so that's the cationic, and this counter ion for is silicon. So this reagent is somehow helps to make the addition of this reagent and this reagent to form compound 16. So basically at this position uh, here, the addition the new bond is getting formed. So here you can play with the mechanism how this bond is formed. So it is given in the this paper. So this was the some of the examples, particularly from this photosynthesis chapter. So if does anyone have any doubt that we can discuss now? Or also, I will also keep some more examples from this one. So, meantime, if you have any doubt, you can just ask me. Here again some examples and which involve quite uh, good kind of reactions that I will show. Basically, we have already discussed the some uh, Wittig reactions. So probably Wittig reaction we have discussed or not, I'm not sure. But anyway, we can show you here. So, first, what is the Wittig reaction? Probably that reaction we haven't really discussed. So basically, Wittig reaction is the in which the this kind of ketone it can be converted into the stereochemistry. So this can be converted into the this sort of this is the R, right? So we can convert that Wittig into, so this is the R1, R2, and this is R3. So we can prepare the ketone to basically this is the new bond is formed and by using the Wittig, and we have to here in this case we need to use the CH2, right? So this is the entire CH2, 1, 2, 3, and this is again also this is also one center. So basically carbon. So here there is not oxygen, there is obviously a carbon. So this carbon is also a part of this new carbon new group. All right. So for that we need to use the this sort of again CH2 Br. So upon CH2Br, so this reagent in place of the base, that is the let's say in so let's take the any base, so it forms the NN here and the PPH3. So basically it gives the PPH3 CH2 and this remaining side group, and this is the reagent, and this reagent upon the addition of the base, so basically this PPH3 plus and this CH minus. So this will be a Wittig salt. So this Wittig salt react with the these ketones to forms a newly formed this olefin. So if you look at the simple structures, so in general, so if you have any kind of this the let's say we have the CH3, CH2, CH, PH3 plus. So this is Wittig salt. So upon reaction of this one, so we get here, this is the CH2. So This is what we get after completion of this reaction. Also, there are these salts are generally less stable, so this is generally not a bench stable. But if you can put that prepare this in situ PPH3 plus. So upon addition of the base, so base basically abstract the proton from here, and this proton is abstract base abstract the proton this, and it forms the anion or the carbon. So basically this is the C negative and PPH3 at the P positive, and this is the Wittig salt. Also there are some other examples of these Wittig salts like CH2 PPH3, and so basically this Wittig is the, so here are CH negative P PH3 positive, and this Wittig particularly this is the stable Wittig. This is stable Wittig salt. So this is how the Wittig reaction works. So if you add this Wittig salt on the same product, same the starting material again. So let's say this plus this Wittig salt, then it will give the double bond. This will be C. That's the R. Sorry, here, right? So this is how we can able to prepare this sort of, and this is the H. So forget about the exact stereochemistry here, but this is the new bond is getting formed, so which is a double bonded one, and depend upon this E and Z stereochemistry, it generally depends upon which Wittig salt that we are using. Generally, the stable Wittig gives the trans, that is the, sorry, not trans, particularly the E geometry. So this E will be formed with the stable Wittig, and generally, I will not comment on that. What does the sorry, the less stable Wittig salt which give the, whether it give the cis or trans? But yeah, basically these are the this is how the Wittig salt forms a new carbon double bond from the carbon oxygen by cleaving the carbon oxygen double bond. So in this case particularly, you can see here added the LiHMDS, then the this is the PPH3 CH2Br, this is the Wittig salt, and how this works. So in this case, LiHMDS, that's the base, and this base basically abstract this proton from this hydroxide. So it gets here, this bonds open up, and it forms the intermediate. So you can see here OH. Now this OH and, sorry, this both are OH are protected. This double bond, and there will be hydrogen. So it forms a aldehyde. So there was obviously one hydrogen was there, right? So it forms the aldehyde. So from this aldehyde, so this new beta I will draw in the some in some better way at least, just to understand. So upon addition of the LiHMDS, that's the base. So upon addition of the base, so the compound 9 is converted into the OH, and here is converted into the aldehyde, and this remaining group will be remain as it is with the same stereochemistry. And further, the reaction of this entire C11 H23 P PH3 Br minus, right? Because it was plus, so Br minus, that's it turns in the form salt form. So it gives the which is the product is forming. This is the entire the chain C11, whatever it is, right? That's the entire chain remaining here. And particularly here, uh, E and Z both isomers are formed. So the stereochemistry here, both E and Z is formed. And further, upon reaction with the palladium on carbon and triethyl silyl hydrogen in the methanol. It gives the reduction of this double bond. So they have reduced this double bond also, and further added the DMP. That's obviously this hydroxy group is getting oxidized to the corresponding aldehyde. And then again here you can see the methyl magnesium bromide, that is the uh, reagent, and which obviously attacks on the this negative charge attack on the aldehyde, and this is form again the alcohol. Once this alcohol is the they have used for uh, some purpose. For particularly this it is from one of the total synthesis of the one of the alkaloid. So this is how they have used the here the example of first example of the Wittig reaction. Then this is the example of the reduction of the double bond. So in place of this double bond, this selectively they reduce the carbon double bond by using the palladium carbon without affecting the ether linkage, right? Or the alcohol group. Further, it is the oxidation reaction, DMP oxidation, and they did the oxidation of alcohol to the corresponding aldehyde, followed by the addition of the Grignard reagent. Again, here it is a carbon-carbon bond formation, new nucleophilic addition of this Grignard, and it converted alcohol, and this alkyl group is entirely attached. So it is also one of the good example to know different reactions. All right. So does anyone have any doubt up to here? So I will take few more examples in from the similar kind of reactions. So please feel free to ask any question if you have any, any doubt here. So you can ask that anytime. So if you look at the continuation of the same reaction, so we'll reach up to some of the master products. So we'll discuss that as well. So in this case, right. So what they have did with these 13. So further, you can see here this DMP they used again oxidize this alcohol form. So this again oxidized to the corresponding alcohol. Further, the ozone lysis, obviously, this entire the terminal it forms ozone lysis. It goes to the here in this case, you can see they have added the NHCO3 and DMS and DCM methanol. It stopped at the aldehyde stage. But there was earlier example that we have seen. So I will go back to that example. In that case, it was not stopped at the aldehyde stage. So where is the example? Right. So here is the example. So you can see this directly converted here from here to here. Initially, it was converted to the aldehyde and then to the acid. And after going to the acid, then this hydroxy group attack on the acid and it gets formation of the ester. So in this case, you can see the reagent combination, and in the in the present case, you can see the reagent combination. So there was O3 and DMS was added at the same time, but in this case, it's not the case. So this aldehyde stage it stops. Also, they have added this NHCO3. All right. So once they stop aldehyde stage, then they have added the KOH. So what is the role of this KOH? So if you look at the entire alkyl chain, and this is the group. So particularly these hydrogens and these hydrogens, there are two different type of hydrogens. They are reactive. Further, this is also one of hydrogen that also reactive. But if you look at the hydrogen which is attached to the hydroxy group, that hydrogen is more reactive compared to the other four. So that's why this hydrogen is attracted, followed by addition of this hydrogen to the aldehyde, right? So better for better understanding, I will just clear all this. So basically, it is example of aldol, right? So this hydrogen abstracted. And once it abstracted the negatively charged form, so that negative charge attack on the aldehyde, not on the ketone, because obviously it will not attack on the ketone, because it is quite in the vicinity, and the ketone itself that not on the ketone of the other molecule as well, because the aldehyde is more reactive compared to the ketone, and this negatively charged attack on the ketone and gives the cyclization. So this entire cyclized product is getting formed with this reaction. So interestingly, you can see this the ketone and this aldehyde. It is important to note the stereochemistry of the aldehyde. So you can see this both hydroxy group was on the top side, and they are attached with the protection the protecting group. That's why the stereochemistry will be unaffected in their case. But once this enolate is formed and when it attacks on the aldehyde, it attacks from the top side, and the corresponding alcohol form, which will be the directing on the bottom, that is the beta, sorry, alpha direct, alpha orientation of that alcohol will be there. So this is the example of the aldol. It's the intramolecular aldol, and yeah, with this one you can get the formation of this compound 6. So if you look at the how they have again used that compound 6 further. So I will pull out that steps here. You can see quite interesting this organic chemistry, right? Because we can play with the from one molecule we can prepare another molecule, from another we can prepare some again another molecule. So here also this alcohol 6 has further converted into uh, the hydroferrone A12. So this is the hydroferrone A12. So obviously it is a natural product. Probably some ferro, I don't know how this generic name comes from. But yeah, we'll see the synthesis. So further, we have this alcohol 6 now in hand. Upon addition of the LiHMDS and the PHACBr, so that's this sort of step that we already seen many times. So they use for the formation of the alpha beta unsaturated double bond to the ketone. So here also do the same. The first step was the PHACBr addition, and then H2O2 the elimination. It gives the compound 15. And further, upon addition of the 5 normal HCl, THF, and 40 degrees Celsius for 2 hours, this entire both hydroxy group is getting deprotected and give the formation of the product A12. So that's the final. Right. So this is how like interesting steps involved in the formation of this product. So I hope you have enjoyed this video, last lecture. And so in this video, we have already seen much synthetic application of our whatever we have studied in this course. So we'll stop here for today. So if anyone have any doubt, please let me know right now, because from the last week, we will not be conducting this session. So this was the last session, and for all of you, best of luck for your examinations. Any doubt as of now? I will stop here for today. So thank you so much for your cooperation throughout this course. So best of luck for your examination. I hope you will perform quite well in the examination. So we'll stop here for today, and thank you.